Whether you are observing a raging whitewater rapid or a quiet trickle from a garden hose, every drop of that water obeys an absolute physical law. Mass can neither be created nor destroyed. It might look like pure chaos on the surface, but underneath, the movement of every single water molecule is dictated by a strict set of mathematical rules. The continuity equation is the mathematical blueprint for this behavior. We will derive it step by step from the ground up. Understanding fluid mechanics requires translating the physical reality of moving water into precise mathematical language. To write that math, we first have to decide how we are going to observe the fluid. One option is the Lagrangian method, where you try to track the precise path and speed of one individual fluid particle as it travels through space. In practice, doing this for billions of molecules is practically impossible. The Eulerian method offers a more practical lens. We observe a fixed region in space and measure the flow passing through it. Establishing this fixed Eulerian control volume is the mandatory first step before any fluid flow mathematics can be written. This diagram shows that control volume as an elementary rectangular block of fluid, a parallelepiped, anchored at a specific point in a 3D coordinate system. On the x-axis, mass entering the left face is density times velocity u times area. As fluid travels, conditions change. Mass leaving the right face adds this rate of change. Subtracting the leaving mass from the entering mass isolates the remaining mass inside. This result captures exactly how much mass is left behind. If the flow slows down as it crosses the box, that missing fluid is now stored inside the volume. We then apply this exact same logic to the y-axis, using velocity v, and the z-axis using velocity w. This textbook equation compiles it all. It states that the sum of the mass changes from all three directions must perfectly equal the rate at which mass is increasing inside our fixed box over time. This single equation accounts for mass conservation across every direction simultaneously, forming the basis for analyzing any complex fluid system. We can use standard engineering assumptions to simplify this. The first is steady flow, meaning the overall flow characteristics do not change over time. Under steady flow, the time derivative becomes zero and vanishes. Think about what happens to the math if the fluid is a liquid, meaning it is incompressible and its density never changes. If density is constant, what happens to the remaining terms? Because density is constant across all axes, it can be mathematically factored out and completely removed from the equation. This leaves us with an elegant, streamlined 3D expression. Civil engineers can solve complex problems efficiently because they are usually dealing with steady water, allowing them to mathematically ignore time and density variations. This diagram shifts our perspective from a 3D coordinate plane down to a practical one-dimensional flow inside a pipe, known as a stream tube. For one-dimensional, steady, incompressible flow, our complex math reduces to this: discharge equals area times velocity, and that value remains perfectly constant at any cross-section along the pipe. The math matches physical intuition. If the area of a pipe shrinks, the velocity must increase to force the exact same amount of mass through the gap. To summarize, we started with the absolute law of conservation of mass inside an Eulerian control volume. We then assumed steady flow to eliminate time and incompressible flow to eliminate density, arriving directly at A1V1 equals A2V2. Real engineering power comes from seeing the physical volume behind the formula. When you understand the derivation, the equation becomes intuitive.